Welcome to Pomodoro Joe for Monday, July 17th, 2023. As you can see, I did not do yesterday's problem, so I owe you one. We'll come back to that at some point. All right, today we're doing LeetCode problem 445. Add two numbers 2. This is a medium problem. You are given two non-empty linked lists representing two non-negative integers. The most significant digit comes first, and each of their nodes contains a single digit. Add the two numbers and return the sum as a linked list. You may assume the two numbers do not contain any leading zeros, except the number 0 itself. All right, and then we have some examples. We've got two linked lists, and you can see we add 3 and 4 and put that in the ones column. Then you do 4 and 6. You add a 0 here, you have to carry 1. So that's 5, 6, 7, 8, and then 7, and here's our output, another linked list. All right. Pretty straightforward. So for this, you need to know a little bit about linked lists, and you need to know a little bit about stacks, I guess. In my case, I'll use a stack. You don't have to use a stack, but we're going to use a stack. So let's put 25 minutes on the Pomodoro timer, and we will get started. All right, so a linked list is just a data structure that has nodes, and each node contains some data. In this case, it has a value, which is just an integer, and it also contains a pointer or a reference to the next node in the list. So this will be our head of the linked list, and it will point to the next node. Now the next node will contain 2, and it will point to the next node. That contains 4, and it points to the next node, which contains 3, and its pointer to the next node will be none because there are no more nodes. So that's a linked list. Now the thing with linked lists, we're given the head of the linked list. Now we can only really traverse the linked list in one direction. We can only go down the list to the tail. So this is called the head, the end is called the tail. So we can really only traverse the linked list in one direction. That's going to be a problem for us because what we really want to do is add the ones first. As we can see in this case, we might have some carry, so we need to add the value further to the right first in order to know if there's a carry for the value to the left of that. So it's going to be a little bit tricky. We can't just traverse these lists and add up the values. The other thing we notice here is sometimes these values won't have a corresponding value in the opposite list. So this linked list is longer than this linked list, which means that there is no corresponding element for this thousandth placed. Thousandth place. I can't say it. Thousands place. There we go. There is no corresponding number in the thousands place for this linked list. So for our case, I'm going to use a stack. Now you could do this by actually traversing this linked list, flipping the direction of the list, and then traversing it again, flipping those directions back. I'm not going to do that. I'm going to leave our current linked lists, L1 and L2, unmodified, and instead we'll use a stack. So first I'll have some result here, and it's just going to be none, and we'll return our result at the end. All right, so what we want to do is go through our entire linked list and basically push each element onto a stack. So we'll grab this element. We can't really do anything with it yet, so we'll save it for later by pushing it onto a stack. Then we'll move on to the next element. We don't really want to use that one yet, so we'll push that onto the stack. So at the end, our stack will be stacked 3, 4, 2, 7. So basically the top of our stack will be the 3. When we pop it off the stack, the next top of the stack will be 4. We'll pop that off, 2, pop, 7, pop. So if we have two stacks, one for the first list and one for the second list, then the top of our stacks will correspond to these ones place or each corresponding place. So the top of the stack will be ones place. We'll grab those values, add them together, pop those off the stack, create our new element for our result. Then we'll move on to the next. So this will now be the top of the stack. So we'll add 4 and 6, pop those off the stack, add those, create our new element, and so on. So that's how we're going to do this one. So we'll have two stacks. So I'll have stack 1, it's just going to be an empty list. We could make this a deck. We'll just do an empty list for now. We'll have stack 2. All right. Now we'll start with some pointer, so node 1. This will be our head of list 1. So while we still have some node 1, so we'll start node 1, we'll push its value onto our stack, and then we'll make node 1 the next node in the list. So first thing we'll do here is we'll say stack 1. We're just going to append node 1's value. and then we'll make node 1 equal to the next node in the list. All right, so eventually this will traverse all the way down to the end, and node 1 will be null, and this while loop will be done. And our stack at the end will contain all of the nodes in our list 1, and they'll be in opposite order. So 3 will be at the top, then 4 next, 2, and 7 will be at the bottom of our stack. So let's do the same for both of our lists, list 1 and list 2. All right, now at the end here, we should have 2 stacks. Let's actually just print these out. All right, so this won't pass our tests, but I just want to show you what the stacks are going to look like. Oh, I didn't create our node 1. Let's do that here. Our node 2 is just L2. All right, try this again. All right, so after we traverse our lists, we have 2 stacks, 7243, which maps to our first list, and 564, which maps to our second list. Now this is the top of the stack, and it keeps going down the stack to the bottom of the stack. Cool, that's exactly what we want. All right, now we have to do our addition. So for this, we'll just pop values off the stacks. So we'll pop each value off the top of the stack as long as there is some stack, and then we'll add those values together. We'll have to keep track of the carry, so we'll need carry, and we'll have to keep track of the totals. So let's see. So while we have some stack 1 and stack 2, or stack 2, all right, so while we still have some value in our stack 1 or 2, we'll just grab this value. I'll call it V1. Well, actually, we better make sure we have a stack here. We'll just make this easier on ourselves. We'll do it inline. So V1 will equal stack1 dot pop. We're going to pop the top of the stack, so we have to pop at -1 if there is a stack. Else, we'll just set V1 equal to 0. Same thing with V2. So for this, our value for our second stack will be stack2 pop at -1. So popping -1 means you're popping at the end of the list. So that's going to be the top of our stack. So pop -1. If we have a stack, let's see, this should be stack1. And if we have a stack2, otherwise this will be a 0. Now we can just add 0 to anything to get that same thing back. So this should be pretty safe. Okay, now what's next? I guess we have to get our result. Oh, I need my carry. I'm not keeping track of that. So let's add a carry out here. All right. Now we add V1 and V2. So our val will just be equal to V1 plus V2 plus any carry we may have had from the previous addition. All right. And now we can reset our carry to 0. Actually, do we? We might have a new carry. So we'll have to keep track of that here. If the value is greater than 10, that means we have some new carry value. So we'll have to reset our carry to 1. And if it's not, then our carry is equal to 0. So I could set it and then reset it. I'll just do that. All right, so we're going to include our carry with this value. So we'll reset it to 0. But if this value happens to be over 10, actually greater than or equal to 10, then we have to reset our carry. And we also want to set our value to just the remainder. So it'll be our value mod 10. So what this will do is this will give us the remainder of dividing value by 10, which basically just gives us the ones place. Okay. And now we have our result. So we have some value. We want to include that in this resulting output. And this is a new linked list. So for this, we're actually creating the ones first, and we're pushing that down. So we basically have to create our result. Let's see. So this result will be some new, what do they call this? List node. And its value will be this value here. And its next node, well, that'll just be the previous result. So first we'll create our ones place, and it will be the end of the list. So we create a new node where its next pointer is none, which is what we initialize our result to here. So that'll point to none. Then when we do the tens place, our result will just be this new node, and its next node will just be whatever we had for our result before. So that's here. All right, so while we still have these stacks, we'll just pop these elements out of the stack, calculate the additions, update for any carries, and then create our new result node and add it to the list. And at the end, we just return our result. All right, I think this works. Let's try it out. And that works. Let's see if we can pass all the tests. Oh, we get a wrong answer. What is this? We output 0. Let's use this test case. All right, so our input is just 5 and 5, and so that should be a 2. So we need, if we have stack 1 or stack 2 or carry. All right, try that again. Okay, so that was my mistake. Totally forgot about the carry. If we end up having basically one more node because we carry that one. All right, let's try this. And we pass. All right, how do we do? We do okay. We beat 56% for runtime and 68% for memory. Not too bad. So we could go back in here and let's see, what could we do to clean this up? This is mostly pretty straightforward. We could probably change these ifs and only check if there is a 1 or a 2, that we can avoid some of this addition. I don't think that's going to save us a ton. What else could we do in here? Well, we could actually flip all of these around and then flip them back. We could avoid the stacks altogether. One thing we could do quickly, I'd like to try, and that's using a deck. So a deck is a double-ended queue. Now, these are just an optimized version of our list, specifically optimized for pushing and popping elements. So we'll just convert our lists to decks instead of using standard Python lists. We'll still use append, but then instead of pop -1, we use pop left or pop right. And we're going to be popping a right. No, it's just pop actually, if I remember. So instead of pop -1, we just pop. That should be the end. Okay, let's try this. Still works. Let's see if this saves us anything. It's a trade-off. And we do far worse, actually. Now we're only at 43% for runtime and 31% for memory. So using the deck didn't actually save us anything here. That's a little surprising, but not terribly surprising. Sometimes using specialized data structures can actually be a little bit slower because you have to initialize these special data structures. All right. Well, I think that's probably it for me. I got to get back to that other video I missed. So the best we got today is a 56% for runtime and a 68% for memory. All right, let's just take a quick look. So we have some time. How did the top one do? Oh, so they do reverse the list. So they go through, they reverse the list, and then they can actually just traverse those reversed lists in the same order or in the normal order and do the sum that way. All right, so maybe reversing the lists will save us a lot of time. All right, that's an exercise for you. Try that out. Instead of using stacks, try reversing the list so that you initially go from left to right. Then those reversed lists, you'll go from left to right, which will now be right to left. And then I would say, to be a good citizen, you should always re-reverse the list before you return so that your inputs don't get modified. But that's just me. All right, well, that's it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.